Module 4, Investigation 8, the inverse of an exponential function. Okay, right away I see the word inverse and I'm thinking the output of the original function becomes the input of the inverse function, and the output of the inverse function is the original input. Up until this point, we have been unable to algebraically solve equations where the unknown variable is in the exponent. Well, maybe not. I don't know if we've done too much of that. We've utilized our graphing calculators in order to solve these equations. I think I remember doing that once or twice. In this investigation, we will learn how to solve these equations algebraically. But first, we're going to do some approximation to try to get a handle on the meaning of the logarithm. 1a, without a calculator, approximate the solution to the following equations. Okay, 2 to the x equals 10. So we want to find the solution. We want to know what is x. Well, I know 2 squared is 4. 2 cubed is 9. 2 to the... wait, that's not right. Sorry. 2 cubed is 2 times 2 times 2, which is 8. And 2 to the 4th is 16. So x must be somewhere in the middle of 4 and 3. We almost had it here. 2 cubed is 8. We just need a little bit bigger than 3. But without a calculator, that's about as good as we can do. Same thing here. 3 squared is 9. We're almost to 10. 3 cubed is 27. That's way too big, but we know that x is in between 2 and 3. Probably pretty close to 2. Describe the process you used to determine your solutions in part A. Well, what I did there was I thought about whole number values of x, and I calculated, let's see, the exponent, 3 squared or 2 squared or 2 cubed, and I found out that I got a minimum and a maximum. I know that my value is in between that range, but I don't know what it is. I hope that's a sufficient description. Determining the solutions of the equations in exercise number 1 involved undoing the process of exponentiation. Instead of raising a base to a power, we determine the power to which a number, the base, is raised to obtain some number. So we already had the output, saying this problem was 10, and we want to know what would be the input. The function that undoes the process of exponentiation is called the logarithmic function. The input of the logarithmic function is the output of the exponential function, the result of raising some base to a power. So the logarithmic function is basically a power. It's really an exponent, or the output of the logarithmic function is an exponent. I think it says that here. The input of the logarithmic function is the output of the exponential function. And the output of the logarithmic function is the input of the exponential function. And notice it says the output of the logarithmic function is the exponent, or we sometimes say the power to which the base is raised. So in the future we're going to write something like this. let's see, now we're not ready for that. Let's keep going to this part here. The standard way of writing the logarithmic function is to write log with a subscript specifying the base to which x is raised to obtain the number that is the input to the function. As an example, log base 2 of 10 equals x is read. Log base 2 of 10 equals x. We can determine the value of x by considering the power that 2 is raised to in order to obtain a value of 10. So here, log base 2 of 10 equals x. That's just another way of writing 2 to the x equals 10. They didn't really say it here yet, but anytime you have a log base a of, so a is just some random number of x equal to k, all that really means is a to the k equals x. So there's our definition of the logarithm. Notice that the output of the logarithm is the input of the exponential. It's an exponent. Rewrite each of the following in a logarithmic form if possible. If not possible, say why. So 4 to the x equals 64. We can simply write log, the base is 4, of 64 equals x. It's helpful to think about this in terms of this definition here. So five to the x equals 1 over 125. We can write that as log base 5 of 1 over 125 equals x. Again, this log is an exponent. It's not possible, like there's no value of x that works here. This equation has no solution. We can't find any exponent that 2 times 2 times 2 is negative 32. So we can't write the log here. It's just not going to work. We can rewrite any exponential equation in logarithmic form. Note that the input to the logarithmic function can only be non-negative real numbers. And you already did that. Let's see. We can rewrite, logarithmic function. For x greater than 0 and b greater than 0, with b not equal to 1, y equals log bx is equivalent to b to the y equals x. So that's the definition that I mentioned earlier. Make sure you can connect those two. Pretty much just the same thing with different symbols. And the function f of x equals log base bx is the logarithmic function with base b. And that's the inverse function to the exponential function. Let's see, rewrite the following exponential equations in logarithmic form. We're going to check the book to make sure the number's right. It's probably problem number 3 for most of you guys. Okay, so we just need to convert these to logarithmic form. This one is log base 4 of y equals x. Just match up the form here. You can come up with all sorts of tricks to memorize that. Today somebody that I was tutoring said that they learned b is the base. I don't remember. Anyways, log this one's kind of weird. Notice that we don't have the correct form, like something raised to an exponent equals something else, but we can get the correct form by dividing by 1.5. And so we can write log base 5 of b over 1.5 equals a. Let's see, this one's kind of interesting. Log base 2 of m equals 4t. If you wanted to solve for t, you could, and just divide by 4. Log base 2 of m divided by 4. Here we sort of need to try the same trick as we did on part B. Let's get it into the correct form. So we have some base, in this case 5, with an exponent equals something else, just like this form here. Base, exponent, something else. Then we can write log base 5 of q over 3 equals 2k. And if we needed, say, k in terms of q, we'll just divide both sides by 2, and that's equal to k. Okay, number 4. I think this is number 4. Without using your calculator, determine / estimate the value of the unknown variable. Okay, here, let's just convert to exponential form. 2 to the y equals 4. And so, I know that 2 squared equals 4, so that means that y equals 2. Next, this means that 9 to the t equals 1 over 81. This one's a little trickier. 1 over 81 is 1 over 9 squared, which is 9 to the negative 2. Just a different way of representing that. And so you see that t has to equal negative 2. Because 9t equals 9 negative 2, these pieces are equal. They have to, t has to equal negative 2. Okay. This one has no solution. We can't have a log of a negative. That would mean that 3 to the k equals negative 2, but nothing will work there. Let's see, 5 raised to s equals 10. What on earth could s be? Well, 5 to the first power is 5. 5 to the second power is 25. I know that s is somewhere in between 1 and 2. But that's the best I can do at the moment if I just want to estimate. You probably know some ways to do this on your calculator, like if you type log of 10 over log of 5, that's the change of base formula, you'll get an answer. Let's see, 7 to the p equals 18. I don't know anything that works there, but I know p is got to be in between 1 and 2, because 7 to the first is 7, and 7 squared is 49. It's somewhere in the middle. Let's see, 3 times log base 4 of 22 equals b. Well, let's think about it like this. Log base 4 of 22 is equal to 1/3 of b. And so, I know that 4 raised to b over 3 equals 22. Okay, running out of room here. Let's take a look at this equation. Let's continue our work over here. 4b over 3 equals 22. Well, I know 4 squared is 16. I know 4 cubed is 64. So that tells me that b over 3 is somewhere in the middle of 16 and 64. Now, if this inequality is true, then I can also say that b is in between 16 times 3 and 64 times 3. So this is 22. Okay, so running out of room, but we know that 4 raised to b over 3 equals 22. Now I know that 4 squared is 16, so b over 3 has to be in between, not 16, 2, and 4 cubed is 64, so it's somewhere in between 2 and 3. Which means it's somewhere in between 6 and 9. So there's our answer for part F. Let's see. 5 to what equals 5? 1. 5 to 1 equals 5. So the answer is 1. Let's see. Let's divide this by -2, so log base 3 of 27 equals z over -2. Convert it to exponential form. 3 z divided by -2 is our exponent, equals 27. Okay. So, actually I know that 3 cubed is equal to 27, so z over -2 has to equal 3. That means z is -6. Recall that in Module 4, Investigation 7, we defined the irrational number e as 2.7182828. Sorry, we skipped that one. A logarithm with base e, or log base e of c equals x, is commonly called the natural logarithm. And we just write ln of c equals x. So there's just this imaginary understood base e right here. When you see the ln, it's the natural log. Your calculator has two logarithm buttons, log and natural log. Even though we can use any base greater than 0 in a logarithmic function, most calculators only evaluate logarithms for two bases, base 10 and base e. The log x button evaluates log base 10 of x and is referred to as the common log. The ln x button evaluates log base e of x and is referred to as the natural log of x. Convert the following to exponential form and evaluate or estimate the value of the unknown. Check your answer using your calculator. So here there's an understood 10 as the base, so I know 10 to the x equals 1 over 100. Well, I know that this is 1 over 10 squared, so I'm just going to match up my bases. That's the same as 10 to the -2. And so 10 to the x equals 10 to the -2. We must have x is -2. And if you typed this into your calculator, you'd get the same thing. Here I know the answer is 2. It's the answer. How do I know that? It's because the natural log is the inverse of the exponential with a base e. So if the input is a 2 for the exponential function, then we put that into the inverse, the output will be a 2. If we want to think about it with the definition, the base here is an e, so e to the k equals e squared. Of course, if these are equal, then k has to equal 2. Natural log of 7 equals t, so let's just think there's a little e. E to the t equals 7. Well, I know t is going to be in between, I'm thinking 1 and 2. Let me check e squared on my calculator. Yeah, e squared is 7.38906, so t is in between 1 and 2. Now if you type on your calculator just natural log of 7, we get 1.94591. So this is the power that if we raise e to 1.9459, we'll get 7. It's actually, this number is rounded off, so I don't think you'll get exactly 7. But the exact answer is natural log of 7. That's the exponent that we would raise e to get 7. Let's see, 10 to the s equals 1,000. I know that's 10 cubed, so s is equal to 3. You type that in your calculator, you can find the same answer. Recall the properties of exponents. Property of exponents number 1, bx times by is bx plus y. Property number 2, and property number 3. You should be familiar with those. I also uploaded a document called Proofs for College Algebra. Let's see, the week before spring break, and it has the proofs of those results as well. It also has the proofs of these results down here, property 1, 2, and 3 of logarithms. Take a second to familiarize yourself with those if you're not already. So basically, if we have a log of two things multiplied together, two numbers, then we can break it up and write the log of one thing plus the log of the other. Same thing for division, but we subtract instead of add. And then if there's an exponent up here, we can bring it down front. Now all of the proofs of these results depend on properties of exponents, the properties right up here. And I'd kind of like to do those in class, but I doubt that we will. The first property of logarithms states that, for example, log base 2 of 4 equals log base 2 of 8. Ask us to find the power to which 2 is raised in order to get a result of 4, and the power 2 is raised in order to get a result of 8, and then add those two powers together. 2 plus 3 equals 5. We could have instead considered log base 2 of 4 times 8 equals log base 2 of 32, and determined directly that 5 is the power of 2 that must be raised in order to get a result of 32. Okay, so all of these are pretty simple algebra computations, just using those rules. Here we have two logs added together. We can combine them as one and multiply. You could write this a little bit simpler, like so. Yeah, that's good. Or you could put 2 natural log x. I mean, we could have got that from here. Natural log x plus natural log x is 2 natural log x. When it says simplify, all of these are okay. It just wants to test if you know the rule. So yeah. Let's see here, log base 3 of 5 plus log base 3 of 2. that is log base 3 of, we have 2 added together so we can combine them as 1 and multiply, log base 3 of 10. Log base 4 of 16 minus log base 4 of 4, we have 2 logs subtracted. We can combine them as 1 and divide, and we get log base 4 of 4, which we know is 1 because 4 to the first power is 4. We could have seen that here. 4 squared is 16, so this is 2. 4 to the fourth is 1, so that's just 1. Let's see, log base 3 of 2 plus log base 5 of 3. You can't simplify that one. That's as good as you can get because the bases are different. Okay, log base 3 of 9 plus log base 3 of 4 minus log base 3 of 6. Well, I know that this is just 2. And log base 3 of 4 minus log base 3 of 6, that'll be log base 3 of 4 over 6, which is 2 plus log base 3 of 2/3. You could have also got a different answer if you had combined these first. You could say that that's log base 3 of 9 times 4 is 36, and then you're subtracting log base 3 of 6, and then you could divide. 36 over 6 is 6, and that's an equivalent result to this one. Let's see, this one you can't do it because you're taking a log of a negative. That won't work. By the way, I think this is probably number 6 and this is probably number 7. Solve each of the following for x. I don't even have an equation here. Okay, now I've got one. If we want to solve this for x, let's just convert it to exponential form, because this means that 5 cubed is 20 or 30x squared. Now 5 cubed is 125 equals 30x squared. I want to solve for x. X is squared and multiplied by 30, so to undo that I can divide by 30. And then take the square root. And so x is the square root of 125 over 30, which you could simplify as the square root of, let's see, 25 over 6, or something like 5 over square root 6. And actually here, when I took the square root of both sides, I should have put a plus or minus, because we have a square here. The positive or negative answer will work. Okay, this one, 10 to the 0 equals 1.5x. So 1 equals 1.5x. So x is 1 over 1.5. It's also the same as 2/3. This last one, I can combine my two logs as 1. X times 2x is 2x squared. Then I know 3 cubed equals 2x squared from my definition of the logarithm. I can find 3 cubed is 27, divide by 2, take a square root. Here I can't put a plus or minus because I can't take a log of a negative x. So square root of 27 over 2. Okay, number 10. I'm sorry, number 7 could also be known as number 8. Complete the following tables. F of x here are our two functions. Let's see, let me start at the bottom here. F of 2 is 10 squared. It's 10 times 10, which is 100. F of 1 is 10 to the first, which is just a 10. F of 0 is 10 to the 0, which is 1. F of negative 1 is 10 to the negative 1, which is 1/10, or 0.1. And f of negative 2 is 10 to the negative 2, which is 1 over 10 squared, which is 1 over 10 times 10, so 1 over 100, also known as 0.01. I see a pattern here. So g of x, the g of 0.01, that's going to be log of 0.01, and what we're looking for is the exponent that we raise 10 to get 0.01, and we know that that's negative 2. And we can fill out the rest of the table pretty similarly. I should probably look at this one for a second. Log of 1. Log of 1 is always 0 because 10 to the 0 equals 1. Log of 10, certainly 1 because 10 to the first equals 10. And this one is 2 because 10 squared is 100. So what we notice here is that these are inverse functions. That's the answer to part C. F and G, the logarithm and the exponential function, the inputs and outputs are reversed. They undo each other. So let's take a look at how that works here. G of f of negative 2. Well, f of negative 2 is 0.01, and g of 0.01 is negative 2. G of f of 0 is g of 1. G of 1 is 0. Yeah, so this is just going to continue. We're just going to get that we have our inputs. After we send an input through the function and then its inverse, we're always going to get the original input. So what do you notice about the relationship? We have inverses. Yay!